Hello. Today I want to give an introduction to my series on essential theorems for harmonic astrology. And in this introduction, what I'm going to try and do is present each of my main theorems as a rule without any proof, but with examples to show how the rules work. So let me share my screen and we can get started. Takes just a minute here. Have to get rid of some panels so I can see what I'm doing. Hold on, almost there. And I think we're ready. Introduction to Essential Theorems for Harmonic Astrology. As I often say, at first glance, harmonic charts seem to be simply a random shuffling of the items found in one's birth chart, but nothing could be further from the truth. Instead, harmonic charts have a very precise mathematical structure, and in this introduction, I'm going to show you without proof and hopefully stated in plainer English some of the rules that govern harmonic astrology. And I'll also show some examples here and there. But first, let me make a few critical definitions. Okay, first definition. If R is a positive rational number, then the angle 360 degrees over R is called the root R angle, and theta sub R equal to 360 degrees over R modulo 360 degrees is called the root R harmonic angle. Doing this modulo 360 degrees simply gives you back a corresponding angle between 0 degrees, greater than or equal to 0 degrees, but strictly less than 360 degrees. It's essentially clock arithmetic. Additionally, R is called the corresponding harmonic. So we have the harmonic and the root R harmonic angle. And I'll note that this definition can easily be extended to include all non-zero real numbers. We don't have it for zero because we can't divide by zero here. But our focus will be primarily on natural numbers and other positive rational numbers. Okay, definition two. If theta sub r is a root r harmonic angle for some positive number r, then a r harmonic angle is any angle of the form k times theta sub r modulo 360 degrees, where k is a natural number. In other words, we get all the r harmonic angles by taking our root harmonic angle, multiplying that angle by various natural numbers, and reducing the result modulo 360 degrees. Notice that for a natural number n greater than 1, and root n harmonic angle theta sub n equal 360 degrees over n, the number of distinct n harmonic angles is equal to n. And they are going to be these angles in this order. Theta sub n is the root n harmonic angle. Then we have 2 times that angle, 3 times that angle, all the way up to n times that angle modulo 360 degrees, which will be equal to 0 degrees. And this last fact will actually be stated later as a rule, as rule number 4. We can actually prove this as a theorem, but here I'm just kind of incorporating it into this definition of a R harmonic angle. Okay, if R is a positive rational number and theta sub R equal 360 degrees over R modulo 360 degrees is the root R harmonic angle, then the set of all R harmonic angles is denoted by H sub R equal to K times theta sub R modulo 360 degrees, where K is a natural number. Okay, an example down below will clarify that. But first, furthermore, I consider H sub R to be an ordered set, where the order of the elements corresponds to increasing values of K until we get to the last element, which is always 0 degrees, and I call this the natural order for H sub R. For example, H sub 3, this will be our set of 3 harmonics in their natural order. It starts with the root 3 harmonic, angle, which is 120 degrees. Then we go to 240 degrees, add 120 degrees to that, we get 360, but that modulo 360 degrees is equal to 0 degrees. Okay, again, these ordered harmonic sets for rational numbers always begin with the root harmonic angle and end with 0 degrees. All right, rule number 1. This is a calculation rule. To find the position of a natal chart point or angle in the n-harmonic chart, we simply multiply that angle by n and reduce the result modulo 360 degrees. And this formula is probably the one that most people use when calculating harmonics by hand. For example, to find the 12th harmonic of 27 degrees Taurus, I can simply multiply the measure of that angle from 0 degrees Aries, that's going to be 57 degrees, by 12, and then express the result modulo 360 degrees. This gives us 12 times 57 degrees modulo 360 degrees, which is going to be 684 degrees modulo 360 degrees. That comes back equal to 324 degrees, which is going to be 24 degrees Aquarius. Okay, now rule 2, if you want the 12th harmonic of some natal point, you don't need to find the measure of the angle that point is from 0 degrees. Instead, you can just find its position in the sign and multiply that by 12 degrees. I find this to often be a useful shortcut in certain situations. So, for example, my sun is at 2 degrees Gemini, which places it 62 degrees from the beginning of Aries. But I don't need to start with 62 degrees. I can just begin with 2 degrees, and things will be simpler. When I multiply 2 degrees by 12, I get back 24 degrees, and that's going to correspond to 24 degrees Aries in the 12th harmonic. Okay, to give another example, this is essentially what we just did, but we'll compute it in a different way. My moon is at 27 degrees Taurus, and so as a shortcut to get its position in the 12th harmonic, I just multiply 12 times 27 degrees. That gives me back 324 degrees, which is 24 degrees Aquarius. When you can use this shortcut, it's easier anytime you're dealing with the 12th harmonic because you don't need to mess with finding things modulo 360 degrees. These products will always be less than 360 degrees, or at least less than or equal to. Okay, rule 3. An angle of 0 degrees remains at 0 degrees in all higher harmonics. Very easy to prove, but also very useful. And as an example, suppose I begin with any new moon chart where the sun and moon are exactly conjunct. So the separation between them is 0 degrees. Then any higher harmonic of this chart will also have the sun and moon exactly conjunct. Because any harmonic times 0 degrees just gives you back 0 degrees. Okay. It's going to be a natural number times 0 degrees. Yeah. All right. Next rule, rule 4. For a natural number n, there are exactly n distinct harmonics. I should say harmonic angles. I'll change that a little later. And any natural number multiple of one of those n-harmonic angles will result in another n-harmonic angle when reduced modulo 360 degrees. So this is very useful to know. For the 3 harmonic, there are only exactly three third harmonic angles. For the 4th harmonic, there are exactly 4 fourth harmonic angles, and so on. Okay, as an example, the root 6 harmonic angle is 60 degrees. That's 360 degrees divided by 6. And the 6 harmonic angles are 8 sub 6 equal to 60 degrees, 120 degrees, 108 degrees, 240 degrees, 300 degrees, and then add 60 degrees to that, you get 360 degrees, which modulo 360 degrees is equal to 0 degrees. Similarly, the root 5 harmonic is 72 degrees, which is 360 degrees divided by 5. And the five harmonic angles are 8s of 5, 72 degrees, 144 degrees, 216 degrees, 288 degrees, and then you end with 0 degrees. In these ordered sets, we always start with the root R harmonic, and we always end up with 0 degrees. Okay, the root R harmonic angle. If I multiply, for example, the 6 harmonic angle by 300 degrees by 5, then I get back 5 times 300 degrees modulo 360 degrees. That is 1500 degrees modulo 360 degrees. And that reduces back to 60 degrees, which is another 6 harmonic angle. Likewise, if I multiply the 5 harmonic angle 288 by 7, then I get back 7 times 288 degrees modulo 360 degrees, which is 2016 degrees modulo 360 degrees. And that is equal to 216 degrees, which is just another 5 harmonic angle. Okay, so the number of, for a natural number n, the number of n harmonic angles is equal to n. You multiply any of those angles by another natural number, you get back just another n harmonic angle. Okay, rule 5 for natural number k, where k is equal to m times n for natural numbers m and n, the k harmonic is equal to both the m harmonic of the n harmonic and the n harmonic of the m harmonic. So this says that when we're just dealing with natural numbers, and you have k as a product of two natural numbers, you could either find the k harmonic all at once, or you could do it in stages. First find the n harmonic followed by the m harmonic, or first find the m harmonic followed by the n harmonic. Okay, now this rule does not hold for all positive rational number harmonics. An example of this is 2.3 times 1.3 times 330 degrees modulo 360 degrees, which comes out to 266.7 degrees. If I tried to do this by stages, first find the 1.3 harmonic of 330 degrees, and then find the 2.3 harmonic of that result, I'm going to wind up with 158.7 degrees, a different angle here. If I do it in the order, first get the 2.3 harmonic and then calculate the 1.3 harmonic of that result, I wind up with 50.7 degrees. All three of these are different. Similarly, it doesn't hold for all irrational numbers, since if I look at pi times square root of 2 times 330 degrees, just multiply that together all at once, reduce it modulo 360, I get approximately 26.15 degrees. But if I do this in stages, first find the square root of 2 harmonic of 330 degrees, followed by the pi harmonic, I get approximately 335.18 degrees. On the other hand, if I calculate the pi harmonic first, followed by the square root of 2 harmonic, this will come out approximately to 87.92 degrees. And you can see they're all different. This could hold for some positive rational number harmonics and some irrational number harmonics, possibly, but doesn't hold for all of them. On the other hand, if we look at a natural number product like 6 equal to 2 times 3, I could find the 6 harmonic all at once. I get back 0 degrees. I could find the 3 harmonic first, followed by the 2 harmonic. When I reduce this all modulo 360 degrees, I get back 0 degrees. Or if I find the 2 harmonic first, followed by the 3 harmonic, again, it's all going to simplify back to 0 degrees. So this rule will hold for all natural number harmonics, which is good because that is going to be what we're dealing with most of the time. Okay, rule number 6. For a natural number n, an angle is an n-harmonic angle if and only if n times the angle reduced modulo 360 is equal to 0 degrees. This is very important. If you take any n-harmonic angle, multiply it by n, reduce the result modulo 360 degrees, you're always going to get back 0 degrees. And you're only going to get back 0 degrees when you multiply an n-harmonic angle by n. And as an example, we could look at the set of 4 harmonic angles, h sub 4 equal to these guys. If you multiply each angle by 4 and reduce the results modulo 360 degrees, which I've done over here, you always get back 0 degrees. Okay, rule 7. House cusps are determined in the n-harmonic chart by first finding the n-harmonic position of the natal ascendant and then using an equal house system. So if you convert your ascendant to some harmonic and you wind up with say 5 degrees Taurus, then the next house will be 5 degrees Gemini, third house will be 5 degrees Cancer, and so on. Now, it would indeed be nice if one could just find the n-harmonic of each natal house cusp and use that for house cusps in the n-harmonic chart, but that doesn't work. Misspelled, doesn't. I'll change that later. For instance, if one were constructing the 2-harmonic chart, then every 180-degree angle would be converted to 0 degrees in the 2-harmonic. That means, for example, that the 2nd and 8th natal house cusps would be conjunct in the 2-harmonic chart since they are 180 degrees apart in the natal chart. And thus, this approach for determining house cusps clearly doesn't work. Instead, one has to use an equal house system. So you see what happens here. We'd like it if when we go from natal chart to 2-harmonic, we'd like the house cusp to all stay in order, right? That would be nice, but that doesn't happen. In fact, every pair of opposite houses will collapse to the same degree, same position in the 2-harmonic chart. So just trying to convert these house cusps one by one to the new harmonic just doesn't work. So that's why we just do the ascendant and then we use an equal house system. Okay, rule 8. If n and m are natural number harmonics, then the root n over m harmonic angle is also an n harmonic angle. Now this means basically that we can reduce rational number harmonics back to natural number harmonics. As an example, let's consider the 3/2 harmonic. The root 3/2 harmonic angle is 360 degrees divided by 3/2, but you can flip this fraction, rewrite this as 2 times 360 degrees over 3. This is going to be 2 times the root 3 harmonic angle, which is 120 degrees. 2 times that gives us 240 degrees, and of course 240 degrees is a 3 harmonic angle. Okay, rule 9. If n and m are natural numbers, then the n over m harmonic angles in their natural order are just a misspelled permutation. More corrections to make. A permutation of the n harmonic angles. I'll illustrate this with a couple of diagrams. The first one will show the natural order for the 12 harmonic angles, and the second one will show the natural order for the 12 over 5 harmonic angles. From the diagrams, we can see that one ordering is just a permutation of the other. So here are the 12 harmonic angles, and I use a blue arrow to indicate the root 12 harmonic angle, which is going to be 30 degrees. And when we go around like this, we get what we call a regular polygon. It's a 12-sided polygon, and each side has the same length. Now, if I do the same for the 12/5 harmonic, that is going to be the root 12/5 harmonic angle is going to be 5 times the root 12 harmonic angle. That is going to be 5 times 30 degrees, which is 150 degrees. So I've indicated that root harmonic angle by the blue arrow. And To get the remaining angles, you add 150 degrees to that and 150 degrees to that, and you're getting back the same 12 harmonic angles, but they are just in a different order. But they will end up with 0 degrees as usual. Okay, so we got our same 12 harmonic angles here, but in a different order from what they were when we looked at 8 sub 12. And this will be 8 sub 12 fifths. Okay, rule 10. If n and m are natural numbers with m greater than n, then the root n over m harmonic angle is the same as the root m over r harmonic angle, where r is the remainder after dividing m by n. Okay, this one really needs an example, but an important consequence of this rule is that in the study of positive rational number harmonics, one can always replace a rational number between 0 and 1, such as 3/5, by a corresponding rational number greater than 1, such as 3/2. That yields the same set of harmonic angles. Also, since 360 degrees, well, before I talk about this, note that if I divide 3 into 5, I get a remainder of 2. So this rule says that the angles you get back for the 3/5 harmonic will be exactly the same as what you get back for the 3/2 harmonic. Now, another way to figure out what this harmonic should be is you divide 360 degrees by 3/5, reduce that modulo 360 degrees to get your root 3/5 harmonic angle. But once you have a root harmonic angle, you can always recapture a harmonic by dividing this angle into 360 degrees. In this case, when I do that, this fraction reduces to 3/2. So the 3/2 harmonic will give me the same root harmonic angle as the 3/5 harmonic. Okay. But if you have a harmonic that's greater than 1, when you divide that into 360 degrees, life is easier because you don't have to reduce the result modulo 360 degrees. You're already going to get back something less than 360. Okay, rule 11. If k is equal to m times n, where m and n are natural numbers, and if theta is a k harmonic angle, then m times theta reduced modulo 360 is an n harmonic angle. I think of this as kind of a cancellation theorem. I multiply this kind of harmonic, m times n, by the number m, and the m essentially cancels, leaving me with n harmonic angles. And a consequence of this rule is that 2 times a 6 harmonic angle will be a 3 harmonic angle. And that's basically because if you take the root 6 harmonic angle, multiply that by 2, you can cancel out 2, and this reduces to the root 3 harmonic angle. Consequently, if I look at 2 times 300 degrees, that's 2 times a 6 harmonic angle. Evaluate that modulo 360 degrees. I got 600 degrees modulo 360 degrees. That reduces to 240 degrees, which is a 3 harmonic angle. Okay, rule 12. This is another cancellation theorem. If theta is equal to j times theta sub m plus k times theta sub m, n, where theta sub m and theta sub n are the root m and n harmonic angles for natural numbers m and n, and let's suppose that j and k are also natural numbers, then m times theta reduced modulo 360 degrees is a n harmonic angle. So essentially multiplying this angle by m cancels out this first term. And a consequence of this rule is that 4 times the sum of a 4 harmonic angle and a 3 harmonic angle computed modulo 360 degrees will be equal to 4 times the 3 harmonic angle computed modulo 360 degrees. Example, if we look at 4 times 210 degrees, I can write 210 as a 4 harmonic angle plus a 3 harmonic angle. Well, I multiply this by 4, reduce it modulo 360 degrees. Um, the first term just gets canceled out, and you can see 4 times 9 degrees is 360 degrees. If you divide that by 360, you get a remainder of 0, so it doesn't contribute anything to the final result. So all we're left with is 4 times 120 degrees modulo 360 degrees. That's 480 degrees modulo 360, which is 120 degrees. Okay, rule 13. If n is a natural number, then every n harmonic angle will be fixed in the n plus 1 harmonic. Rules about fixed points in mathematics are often very important to the theory. So let's look at an example. If I take a 4 harmonic angle, like 270 degrees, and multiply it by 5, and reduce the result modulo 360 degrees, I should get back 270 degrees. That's what this rule is saying. And sure enough, do 5 times 270 degrees. We get 1,350 degrees modulo 360 degrees, and that's equal to 270 degrees. We got back exactly the same angle. Well, we can go even further. If n is a natural number, and if we take a polynomial with constant term 1, evaluated at n, and call the result the m harmonic, then every n harmonic angle is fixed in the m harmonic. Okay, for example, 72 degrees is a 5 harmonic angle. If I take a polynomial with integer coefficients like this one, evaluate it at 5, then that gives me the number 431. And in the 431 harmonic, 72 degrees is going to be fixed. I multiply 72 degrees by 431, evaluate the result modulo 360 degrees. I just get back 72 degrees. And my final rule, I call the fundamental theorem of harmonic astrology. If n and m are natural numbers greater than 1, with root harmonic angles 360 degrees over n and 360 degrees over m, then the root harmonic angle for the least common multiple of n and m is equal to the greatest common divisor of their respective root harmonic angles. Theta sub n equal to this, and theta sub m equal to this one. And as a consequence, if we look at the 4 and 6 harmonics, their root harmonic angles are 9 degrees and 60 degrees, and 360 degrees divided by the least common multiple of 4 and 6. That gives me 30 degrees. That's going to be the same as the greatest common divisor of 90 degrees and 60 degrees. So this rule establishes an important duality between harmonics and root harmonic angles. And this rule also applies to positive rational number harmonics. So if I look at 4/3 and 6/5, the root harmonic angles for these are going to be 270 degrees and 300 degrees. And the greatest common divisor of 270 degrees and 300 degrees is 30 degrees. If I look at 360 degrees divided by the least common multiple of these two fractions, well, to find the least common multiple here, I rewrite the fractions with a common denominator, and then I just find the least common multiple of the numerator over that denominator, of these numerators over that denominator. This gives me 360 degrees divided by 180 over 15, and that too reduces to 30 degrees. And here's another example where both of my fractions are less than 1. I'm going to get back the same harmonic angles, root harmonic angles, 270 degrees and 300 degrees. Their greatest common divisor is 30 degrees. And if I look at 360 degrees divided by the least common multiple of these two fractions, I use the same procedure to get that. And I wind up with 360 degrees divided by 924 over 77. That too reduces to 30 degrees. Okay, now those are going to be the main results, the main rules which in my other PowerPoint slideshows and a more extensive paper I've written, I give rigorous proofs for those rules. But here I'm just giving rules and examples instead of theorems with proofs. But here are some final thoughts. Now, I haven't worried about negative harmonics since they yield negative harmonic angles that can also be expressed by positive angles and positive harmonics. For example, the root -3 harmonic is 360 degrees over -3, which is negative 120 degrees. However, in our zodiac, misspelled zodiacs, their circle minus 120 degrees is the same as 240 degrees, which is the root 3/2 harmonic. Hence, every negative harmonic can be represented by a corresponding positive harmonic. And since every positive rational number harmonic, n over m, where n and m are rational numbers, can be represented as a multiple of the root n harmonic, every positive rational number harmonic can essentially be reduced to a natural number harmonic. Hence, the study of natural number harmonics is what is most important. Also, as one of the above rules shows, every positive rational number less than 1 can be expressed as a positive rational number harmonic greater than 1. And this can simplify calculations and shows that when dealing with fractions, one only need focus on positive rational number harmonics. They're greater than 1. Now, I've also avoided dealing with irrational number harmonics for two reasons. First, they don't always follow the same rules that apply to natural number harmonics. For instance, a natural number multiple of an irrational harmonic angle when reduced modulo 360 degrees will never be equal to 0. As example, consider the irrational number phi, which is 1 plus square root of 5 over 2, which comes out approximately equal to this. And that number is commonly known as the golden ratio. If there were a natural number m such that m times phi modulo 360 degrees were equal to 0 degrees, then that would mean that there exists a natural number k such that m times phi is just a natural number multiple of 360 degrees. But that means in turn that phi is equal to k times 360 degrees over m, and this is going to be a rational number, right? We have a rational number in the numerator, or a natural number in the numerator, natural number in the denominator. That's a rational number, and this can't happen because phi is supposed to be irrational. Therefore, there is no such natural number m that makes this happen. Similarly, as a consequence, it can be shown that the sequence generated by m times phi modulo 360 degrees for m equal 1, 2, 3, and so on is infinite and never repeats any of its elements. You never step into the same river twice. So you're never going to have a natural number multiple of an irrational number giving you back 0 degrees when you reduce it modulo 360 degrees. Okay, and the other reason why we probably don't need to be concerned with irrational numbers at this point is because when it comes to doing computations in the real world, we always use a rational approximation for any irrational number. For example, when computing harmonics, my astrological software uses the approximation 1.618 in place of the irrational number phi equal to this. And this harmonic corresponds to the fraction 1,618 over 1,000, which reduces to 809 over 500. Hence, the root harmonic angle is approximately equal to this expression, and for the most part, this approximation will work well. However, if we multiply our approximation for the root harmonic angle by 809 and reduce the result modulo 360 degrees, then we'll get back 0 degrees, which won't happen with an irrational number harmonic, and that's where things break down. So we can find root harmonic angles for all real number harmonics except for 0, since 360 degrees divided by 0 is undefined. The bottom line is that negative number harmonics can be replaced by positive number harmonics, and irrational number harmonics, while having theoretical importance, great theoretical importance, can in practice be approximated by rational number harmonics. And when dealing with positive rational number harmonics, we can restrict ourselves to those greater than 1, and each harmonic n over m, where n and m are natural numbers, simply results in a permutation of the ordered set h sub n equal to this. Thus, it appears that the natural number harmonics are indeed the most important for us to understand. Okay, that is going to be the end of this introductory slideshow. Found a few more typos I need to correct, but for the most part, it's good. So I hope that gives you a little bit more insight in terms of rules and examples. And if you do look at the slideshows where I get the theorems and take you through the proofs, I hope they make a lot more sense now. And then hopefully, maybe even someday, you could actually read the complete paper I've written. But that's it for now. So for now, I'll just say so long and be well.